computing. Okay, that's the better. Okay, so I gave you the lecture for an introduction to quantum cryptography and entanglement for engineering applications. Specifically, we are interested more in kind of robotic and autonomy area. So we had this lecture, and the lecture will be available also not only on Blackboard on my website, so you can find them in future if you don't have access to Blackboard. Now, I don't want to go through all the slides, but they will be available for you. I just want to refer to the introduction of this or the literature review. So it mentioned about some of the recent area that is related to mechanical system education and quantum technology, which I mentioned about drone-to-drone, quantum key distribution, and space and underwater quantum communications. Of course, there are many research work going on into quantum technologies, sensing, communications, and many other areas, and quantum computing. We are specifically interested in mechanical systems, education, and engineering, okay, quantum and quantum technology. So we are not talking about quantum computing here. There's a lot of literature available in quantum computing, but as electromechanical engineers, we are more interested in these specific areas. Okay, so I will not talk about quantum computing or quantum physics. Okay, so it's more about quantum engineering. And then these two articles are available for you to read: Preparing for the Quantum Revolution, Achieving Quantum Smart Workforce. So in terms of the demonstration that I have for you, the demonstration will be quantum entanglement and quantum cryptography demonstration. But if you remember from the lecture, okay, let me go to the slides here. If you remember from the lecture, we talked about the photons, which is the basis of the quantum mechanics. If we work on photon quantum mechanics, of course, we can work on electron, but we don't have the facility. We don't talk about that. We only talk about photon. And in photon quantum mechanics, we are interested in single photons and also vertical and horizontal polarization of the photons. Okay, so that's the basis of quantum mechanics, or photon-based quantum mechanics. Okay, so two main components, that these are basically optics equipment that we are going to use in our experiments, are going to be a half wave plate, which is also is represented as a gamma divided by 2, half gamma plate, which what it does is if the beam is going through the half wave plate, it rotates the polarization of the photons that is going through based on the how much you rotate the polarizer. Okay, and now this component, let me show you, stop the share. This is basically something like that. Okay, so let me remove my, okay, quickly, I have to remove my background so you can see it. None. Okay, so this is what's called a half wave plate. Is inside, so it's a kind of a like a glass-like inside half wave plate, and you can rotate them. You see the angles that you can rotate. So this is the basis of some of the experiments that we are going to use. So you can rotate this wave plate, and you can basically rotate the polarization of the photons going through this wave plate. So that's one of the main components, and I'm going to talk about it both in quantum entanglement and in quantum cryptography. Now let me go back to the lecture. The second one is going to be a beam splitter. Okay, the beam splitter. So photons with horizontal and vertical polarizations reaches the beam splitter. Polarizing beam splitter reflects the vertical polarization, so photons with vertical polarizations, and let the horizontal polarization to transmit or pass through the beam splitter. And you will see that in the experiment that I'm going to explain. So again, going back to review some of the lectures that we already have, we talked about the BBO crystal. So we have a beam going through the crystal, and it gives us two kind of photons going through what's called signal and idler, and that will basically, these two photons that is generated from the BBO crystal are entangled. Okay, they will be called entangled photons. So they're correlated in terms of their polarization. So the setup that I will be explaining to you is this setup. So the laser, there's a laser source. Laser source will be placed in front of the BBO directly, so that I will not use a mirror in this case. And then we'll have a BBO crystal, which I'll show you. And then the photons, most of them basically the beam goes through, but some of them will also will be created in a cone with minus and plus 3 degrees. And these are the idler and signal beams that represent the entangled photons. Okay, so the photons that are correlated in their polarization. Now they will go to polarizers, beam splitter polarizers, polarizing beam splitters. And today I will only show two detectors which are detecting the entangled photons. I have the other detectors and the polarizing beam splitter, but in this particular experiment today, I will not demonstrate those. So this is the first experiment, and as you see here, we have a laser source. We have the BBO crystal, which I'll show you now. And at the back, we have basically the setup will be like, instead of it directly going to the detectors, which are counting the single photons, we have a filter, which only allows 810 nanometer wavelength photons to go through. And then we have a collimator, which is like a lens focusing the photons through the optic fiber cable to the detector. Okay, so I'm going to show you all this. And then there is a single photon counting module, which is counting how many photons you're getting. Okay, and there's a interface box goes to the FPGA circuit, which counts and find the coincidences of the photons. So if the photons reaching to the sensors or the detectors here, they arrive in a very small time window, like nanosecond range, then we say we can call them entangled. Okay, so this FPGA is going to take care of that. They'll tell us when they receive when the photons reaching to the detectors, are they in nanosecond range window or not? So that's going to tell us about the coincidences. And the FPGA is connected to a laptop, and a laptop running a LabVIEW program, which is showing us the single photon counts from each detector plus the coincidences. How many of these are really entangled? So how many of these are reaching the detectors in a certain window, small window of time? Okay, so this is another, just a view of the setup. This is just a power supply for the detector. Okay, and this is a window that I'm going to share with you soon and show you how the detectors are counting. This is an example of type of coincidences that we get. So so we have 80,002 detectors. I'm not using 4 detectors in this experiment. Another thing I want you to do is a little bit on remote experiment. And I'm going to allow you to maybe, hopefully, to manipulate one of the polarizers. One of the polarizers that I have, half wave plates I have here, which is, I explained earlier, is motorized. So it can be controlled remotely. So I can allow you to access my laptop. We are going to try that. And you can rotate it and see the effect on the count of the photons. Okay, so we'll see how we can do that. So now with this introduction, if you don't have any question, by the way, I also show you, stop the share. I show you the beam splitter. It's just a kind of a cube, like this is a beam splitter, and you'll see that in the experiment.
Professor, I have a question.
Yes.
So how is this system and the collimators, how should I say, addressing the fact that there are stray photons that are just running into the system? Like, how does it detect whether the ones, how does it detect the photons coming from the beam splitter as opposed to just random photons that are in the, like, just premises into
Oh,
the,
so first of all, the light should be off. Okay. So also there are two things. First, I turn the light off, and the other thing is that I have filters in front of the. So that's a good question. So let me go back to the slides. So I place a filter in front of the collimators. So these are two filters in front of the collimators, and they only allow 810 nanometer wavelength to pass. Okay, so when I create here, when the BBO generates the entangled photons, the source of photon is 405 nanometer. After passing the BBO crystal, it will give you 810 nanometer wavelength photon. So then when you put that that filter in front of it, it only allows you to these photons to pass, not other photons that are just you may see in the room. Okay.
but theoretically, couldn't there be like
Yes.
some photons
Exactly.
that are that
Exactly.
length?
Theoretically, it can be. So that can be discussed, but mostly in this experiment, we are expecting to receive. So there's always noise, even if there is a total darkness, the noise can also be from temperature change, even. Okay, not even photons. So these are all the things that has to be taken into account, and they are important. But yeah, for now we don't discuss them the details.
So you don't shield your own body from producing that noise.
Exactly. Yes, that's a good point. Also, everything. So, everything has to be taken into account. So I'm going to stop, uh, and I will now show you the experiment. Okay, in my other laptop. Okay. So this is the setup. It might look a little different. You see in front of the laser, I have a polarizer, which I can rotate, and we can connect it. It's motorized. Okay, it's a rotary motor, which we can rotate and see the effect on the count in the single count of the photon. So here I have the laser, and here this is the video crystal. From here, there are some extra components which I'm not using, but these are the main components. So this is the filter, 810. This is the collimator going through the fiber cables. Put this back in front of it. And going to this side, this is the FPGA, which is counting the photons and coincidences. This is the detector. It's called Excelitas. This is the brand or the name of this technology. Here on this side, I have, here is the power source for the detector. So now, let me show you what we are expecting. By the way, check out my full. Okay, so this is the program now, LabVIEW program that is going to show you the counts. So let me start it. Because the light is on, the counts is going to be a lot of counts now, as you see here. So it's in the range of millions, basically. But let me turn the light off and turn the laser on. Okay, now these are the entangled photons. I'm going to do some fine alignment. As you see, A and B, the detector A and B are showing you something in the range of 40,000, 80,000, but we're expecting to be in the same number, same range. This is not too, they're not the same, so I'm going to make some slight alignment. Alignment is not an easy job here. So let me see what I can do to make it better alignment. So they have to be equal numbers, almost. Okay, so I can do a little bit. Okay, so I think that's not too bad. It's not. We're expecting, ideally, we're expecting about 100,000 maybe photons, but I think I'm happy now for now, which we get about 40,000 on one of the detectors, 40,000 on the other detector. Should be much better than that. But for demonstration point of view, I think it's not too. By the way, can you hear me? Maybe I should change to.
Yeah, we can hear you.
Yeah, we can hear you.
Okay, maybe I stopped. Stop.
So, Professor, when you're trying to align
Okay,
it
I
right
think
now,
you can hear me better now. So let me do a little bit more fine alignment. Maybe I can make it better. So even you see, I just every small movement can make this big change in the numbers. So these are not really okay. This is not good. That's better. Okay. Crashed. Okay, I think that's not too bad. Let's just stop here. So each one is about 40,000 photons counting and about 200 coincidences. So we can think about them, think of them as entangled photon. 200 of them are reaching in the small time window of nanoseconds or 10 nanoseconds. Now what next I'm going to do, I'm going to place a polarizer in front of the laser. So this polarizer, if you remember, I said the source should be 405 nanometer. And also the polarization of the photon reaching to the BBO in this particular case has to be horizontal, okay? So I don't discuss that in detail, but imagine that it has to be horizontal polarization reaching to the BBO. And in this case, I'm going to put a polarizer in front of it, okay? Which only allows basically to rotate the polarization and see how it affects the result. Okay, I'm sorry. So this is now, I'm placing the polarizer in front of it, and now I'm going to rotate the polarizer. Instead of rotating by hand, I'm going to rotate it by a program because it's motorized by program. And then here you'll see also if we can somehow, right, so let me see. So the next thing I want to show you is program for rotating the polarizations. Okay, share. What am I sharing? Share. Okay, so this program is made to rotate the polarizer, but let me change. Okay, is it working? COM3. Let me try one more time to see. COM4. Connect. Okay. So the problem is now I think I have connected the motor. So I can now rotate the motor and look at the polarization, look at the number of counts, how it's going to affect the counts. But the problem is, I think oh no, it's okay. We are good. We are in business. Okay, so let's change the, let me see if I can show this at the same time. All right. Okay, so let me share my screen. On one side, I have the counts. On the other side, I have the polarizer, which I'm going to rotate. So at the moment, the position of the polarizer is 0. So let me rotate it to 90 degrees, see if it's going to affect. So let's look at the counts now. The counts are 11,000 or 9,000 roughly, and the coincidences are very small, I guess. Coincidences are about 10, 15, but don't worry about that. That's because the polarizer is not aligned. Now let's see if we can improve it. So let's rotate it 90 degrees. Okay, did I make it better? I did. Look at that. I rotated the polarizer 90 degrees and now it went up and the coincidences went up. Okay, so now let's
Professor?
change that to 180. Okay, I hope I could show you both at the same time. This doesn't. So, move. Okay, not so much change for some reason. 27,000. So let's go back to 0. Move. Okay, let me see. Okay, not so much change for some reason. 90. Oh, changing. Okay, I'm not sure what, because I usually rotate them by hand and I can find the best angle for the best result. But here I can see it's working, but -90 degree. Okay, so now let's just do an experiment. So so you can see that the counts are changing by rotating the polarizer, because I'm rotating the polarizer and I'm expecting the at some same certain orientation of the polarization, I can increase the number of counts or photon counts. So let me give somebody an access. So one of those guys who is working in this experiment, who is available now for your senior design project, who is available today?
I think we're all here, Professor.
Huh? Anybody? I hear Jack was here. Jack, are you available? Hello? Can you hear me?
Hey, Professor. Sorry, I had an audio issue.
Hello?
Yeah, can you hear me?
Did we stop?
Hello.
Hello? Jack?
Hello.
Oh, I'm sorry. I'm sorry, I couldn't hear you. Who is available from the group?
I think Francisco called out as well. I don't know
I'm
if he
sorry,
wanted to.
Francisco. Okay, I'm sorry, I couldn't hear you. That's my fault.
No
Okay.
problem.
Francisco, you go ahead first, and then I ask Jack also. So let me see how I can give you access here. Ask. I'm going to give you access. Oh, I think because I have to give access from the other laptop. Let me see more. First, okay, I'm going to make Francisco co-host, and I'm going to Francisco, can you hear me?
Yes, I could hear you, Professor.
Okay, thank you. And now let's go to, I want to give you access to the laptop, but for some reason I cannot find it.
Maybe start with share screen first and then see if that gives you the option.
Oh, okay. So maybe, let me see, maybe you can. Oh yeah, you're right, you're right. Good point. Let me share screen and then, good point. Share my screen. Now let me see if I can give you computer. So let me make the other laptop. Maybe let me make my other laptop to be the host.
I just sent the request for remote access.
Oh, you did?
Yes.
Oh, excellent. Good job. Okay. So now can you access this laptop now?
It says I can control your screen. I'm just gonna.
Okay. So, oh, good. You have access now.
Okay.
Excellent. So go to the position when you say it says move. You see it says move to degrees, absolute degrees.
Give me a sec. Yeah, where it's at 90.008.
Go here. Go down 90 degrees. Can you change that to 0 and move? And then check the result on the other window. See if it's going to. Yeah. So you rotated it now. Oh, okay. So click on that small arrow on the top in the menu below edit. Good. Okay, now you can see, let me do a little slight alignment in terms of, okay, just want to make the, okay, I did a slight alignment. Now we get about 46,000 each detector and 200 coincidences. Now change the position to a different angle and see if it affects, this 40,000 will be changed. So let's change that to 30 degree maybe. Yes, a good one. Let's check. Yes, it's reduced.
Yeah.
So we are changing the polarization of the photon going through from the laser to the BBO crystal. BBO crystal, the maximum it would be if the polarizations are horizontal in this particular case, okay? So then you can manipulate that and find the best orientation for maximum number. So let's find the maximum, the best orientation for maximum number of photons. So 30 is not the maximum. So let's find another.
Let's see. Oh, we already had strike 90. Can we do like 180?
Yeah, let's try. I'm not sure. I usually do it manually. It didn't change much really. Let's try another. 90 maybe. That's a good one. That's not too bad. So let's see if we can make it better. Maybe make it 100, just a slightly larger. Okay. Yeah, that's
Okay.
better. It was 40, now it's 50. Let's make it 110. So let's find the optimum orientation. Let's see. No, went down. That's a strange, went down again. So let's go back to the one that was 100.
Yeah.
Let's see if it goes back, or maybe we lost the alignment. If I slightly touch the table.
Yeah, we lost the alignment. Now it's at 40. Oh, wait, it's there.
Oh,
At
okay,
49,000.
it ran
Yeah.
back. Yeah. I'm just touching the table, and the alignment is so sensitive that as soon as I touch the table,
Oh,
my
okay.
movement can make changes. Okay, the program stopped. So can you run the program one more time? Okay. Oh, good. Now let's make it again 110 to see if it improves. Let's see. No,
No, it went
oh,
down.
you know what? Because it's a mechanical movement on the table, and maybe it's vibrating also the system, vibrating everything, and it goes out of alignment. Maybe just a slight movement that we have here. That is another possibility, because let me see if I can make it better again. By hand. By hand is a little bit. Okay, so let's keep it here. Now let's go back to 100.
Okay.
And see if it again make it better a little slightly. Yeah, actually it's very, yeah, that's working very well. So that's the optimum, I guess. That's the optimum. So make it 90 now again. That's the best polarization orientation that gives you maximum number. So I don't explain really the detail why is this happening, but there is a orientation from the laser that always gives us the maximum number of counts, which is very interesting, and that depends on the BBO, what's called phase matching. So let's go back to 100. So that's, I think, the optimum. That's the optimum orientation of the polarization of the photon, which gives you the maximum number of the photon counts. I think that's the best. Excellent, very good. Thank you, Francisco. So Jack, you can repeat if you like, see if you can find a better angle. So now who is the host? You are the host, I'm the host. Let's give it also, let me stop this and also ask Jack to do this. Because
I just gave up remote access.
You did?
Yeah.
Okay, is Jack still here? Where is Jack?
Yeah. How do I take remote access again?
Okay, let
Go
me
to the
see.
top of the screen. Once you start share screen, to the top of your screen and request remote access.
Okay.
Gotcha.
So the view options.
Oh, okay, I can give you. I gave it to you. I gave it to you.
Okay.
I gave access. So now you go first thing, go to the program and run the program. Click the small arrow on the top. No, that's yeah, perfect. Excellent.
Right here. Gotcha.
Yeah.
Oh, okay.
Run the
I'm seeing
program.
it just isn't responding as I expected.
Yeah.
Okay.
Okay, excellent. So now see if you can find a better, maybe you can slightly rotate it or up to find the orientation on the other program that gives you the maximum number. You can start from smaller angles or larger angles, just trial and error. On the other program, you see there is the angle here. Rotate the polarizer in here.
Angle.
Here, yes.
I'm not seeing where the here is.
Oh, sorry, here. Here.
Oh, okay. My bad.
Yeah.
Gotcha.
Yeah. So let's see if we can increase that 49 number of counts to, you can do smaller angles. Okay. Okay, so that looks good. Looks good. So change it to 95 to see what happens. No.
So it's gone down.
Yeah,
So
gone
that's-
down. So go on 105 maybe. No, I think
It's
the
down as well.
100 number is the best. What do you think? Sorry, I just opened the door.
Yeah, this seems good. 102 degrees. It's a little high. But actually, it's kind of stabilizing. Oh, there he is.
Oh, you're running LabVIEW too?
Yeah, LabVIEW. So they have remote access now. They are running it. So I have a polarizer here, rotating by motor. This is a motorized.
Are you doing it through Zoom?
Yes.
Hey, Dr. Herder.
Hey, Jack.
Just,
Yeah. Oh, it stopped. Did I click something?
just running again. Click.
Okay.
Run the program one more time. So this is a motorized rotator.
Yeah.
There we go. Yeah.
Okay, excellent. So what do you think is the optimum angle?
It seemed 99.5 was good, and then it's somewhere between like 100 and 102, I think.
Okay, interesting. Okay, thank you,
Try
Jack.
101. Yeah.
Yeah, try.
Sure. Or 100.5. Because we're going for 49,000, right?
Yeah.
Yeah, this is pretty steady.
Okay. Now, okay, thank you. That's excellent.
Cool. Yeah,
It's
thank you.
interesting. I was in the lab and Professor Herder was here.
Mm.
He just came into the other room, so I called him to see this. Now you can also, yeah. So you think that is the optimum? Okay. So now in your group that you're doing this experiment for as a project, anybody else would like to try it? In your group or Francisco group who are doing this project? Okay, so you can do it later on again.
Maybe
We can
Joseph?
Who is that?
Maybe Joseph?
Joseph, is he here?
Yes, I just have two
Go ahead.
devices on.
So let me give you remote access.
Due to the one that says Joseph Espinoza.
Let me see, Joseph, yes. I gave you, did you get access?
You can control far by screen. It says I can.
Okay, go ahead and try to change the
Oh.
position.
Yeah.
Okay, if you can start from maybe smaller values, like start from 30 or something, 45 maybe, see, from 0
Okay.
maybe. You start from 0, see what's the best,
Hmm.
45, 0, or anything you like.
I'll do 45.
Okay, so let's look at the results. It went up or down. Oh, sorry, I have to, I have to give you, I forgot to give you
Oh,
the,
yeah. I'm okay. So I got everything running on this thing if you want.
I'd like to show them next week.
Okay.
Oh, sure, thank you very much. Thank you. Okay, went down.
Yeah, I believe so.
Okay, so now see if you can find another angle that is optimal.
Do 60. Still pretty
Okay.
low, huh?
No, yeah, go up.
Try 90.
Run
Oh,
the
it's
program one more time. Stopped. Click on that arrow and below edit.
oh,
Yep.
the arrow.
Yeah. Okay,
Oh,
that's
okay.
better. That's better. Go up.
Let's try 120. Still pretty low.
What happened? Went down suddenly.
What's going on?
Find maybe 100 or 110.
I'll try 100, yeah.
Oh, excellent. I think that's the best, I think. Or around 100, a little up or down, I guess.
We're doing for AB, correct? So about 260 something.
Exactly. So AB is the easiest way to find out. So when it goes up, is the number of coincidences between A and B. Okay.
And why is it that we have A prime and B prime?
Oh,
as
these
well?
are in total, we will have 4 detectors.
Oh, okay.
I'm only using 2 of them, but hopefully in future, I will show you if I improve my setup, I'll show you with 4 detectors if I have. I need another BBO crystal, which I've ordered. Hopefully, if I receive it before the end of semester, I will demonstrate to you how we can use the 4 detectors and what is the magic happening in the quantum entanglement when you have 4 detectors and re-rotate the polarization of one photon and the other one will rotate without any kind of communication between them, which is the entanglement, basically. Okay, so thank you, Joseph, and thank you, everyone. So anybody else would like to try it before we move to the next experiment? Okay, so if you don't want to, I'm going to demonstrate now quantum cryptography for you. So if you like, we can stop this now. And I give you again a brief introduction about what we talked in the lecture about cryptography. So I turn off the laser. I turn off the detector. Okay, I turn them off. Shall I keep my glasses on or how do you think? So, okay, let me turn this. So glass on or off? What do you think? Looking good?
On.
On? It's
For
cool.
sure.
Okay, thanks. Okay, let's go back to the lecture notes. Host disabled participating screen share. Okay, now I have to give myself. Hello, can you hear me? Can you hear me?
I can hear you.
Okay, thank you. So I lost the host. Okay. So we talked about this experiment a little bit and show you basically just a demonstration. And now quantum cryptography. So I'm going to demonstrate this experiment for you. Is again based on half wave plate again and beam splitter. Now here we talked about Alice and Bob, and we said that Alice can send photons with different polarization by rotating her polarizer. Bob also has a polarizer, which I'll show you today now. And there's a beam splitter. So by adjusting the angles of the rotations of the polarizer, we can create combinations of the horizontal, or to create horizontal or vertical polarization. So if we create a horizontal polarization, let's say we set the first one to 0, second one to 0. If first one 0, second one 0, both of them create horizontal, so the answer is 0. We just simply add them. 0 plus 0 is 0, and gives you 0 transmits. Now if I use 90 from Alice and 0 in Bob, then 90 plus 0 is 90 with reflect to, and gives you 1. So that becomes digital 1. Now if I choose negative 45 plus 45 gives me which one?
0.
0, thank you. So it transmits, goes to this detector, and this detector has a small light on it. It will light up and you will see it now. Now, how about if I use 45 and 45?
90.
90 will go to
Reflected.
reflect, correct, you're right, thank you. So this table gives you a summary of all the combinations. So if you choose anything that is in between, is 50-50% chance, so it will be ignored. But anything that adds to 0 or 90, then we can take into account as digital 0, digital 1. And by the way, I noticed that when I give you this lecture last time, this table was not correct. So I had to update the table, and now it's corrected. So again, get the latest lecture from Blackboard, and in future you can also get it from my website if you need it. And that has a correct values here. So even if you check a Toll Labs manual, is wrong. And I contacted them and I told them, I noticed that for some reason I didn't notice it before, but so they're going to correct it. So there's also some more information if it's the intercept. I don't discuss that, there's no time. And then eventually we can put everything that we have on robots, and maybe this kind of communications of 0, 1 can be communicated by between robots. So we can talk about that now. So let me stop the share, move the laptop to the other side. Okay, now, how much you see from there? Okay, so this is what I just talked about. So this is Alice. Alice has a laser, and the polarizer. If you see, the polarizer has angles which can be rotated -45, 45, 0, 45, and 90. And basically, this is what you just did using a motorized polarizer. So, what you were doing in that program, you were rotating, instead of I rotate this by hand and rotating the polarization, you were doing that using a motorized kind of system, rotating it by changing the angles. And this is the laser again, one more time. So on the other side, so this is, again, Alice, this is Bob. On Bob's side, you have another polarizer, or half-wave plate, we call it, or that's the one. And this one has 0 and 45 in this case only. 0 and 45. Can you hear me? Everything going okay so far? If you don't hear me or you don't see, let me know. It goes to the beam splitter. See the beam splitter there? And then we have two detectors. Detectors are going to light up based on the, if we have 0 or 90. So let me try just one as an experiment. So let me set you up here. So I'm going to just show you the combination of 0 and 0, 0 and 0. And I'm going to send the laser pulse. Did you see that or you don't see? So let's see which one lights up. 0 and 0. Can you see?
Yeah, the one on the right.
Okay, so it basically passes, yes? 0 and 0 transmits from the beam splitter, which is here, and goes through. Okay, so is it clear? Any question? So let me change that now to going back to Alice, and let's change that to 90 and keep the other one as 0. Let's look at the answer. So which one do you expect to turn on? This? Zero or 1? At the moment is 90 degrees. Any suggestion? Okay, so.
I think 1.
Correct, 1, you're right. Can you see that? Okay, so I'm sorry, are we going over the time? Yeah, okay. So I don't want to take a lot of your time now. So this is the setup. From there, so the idea is now, once we have the setup, there's also possibility of the intercept. This intercept comes here in the middle and try to steal the information. But then the idea is that in the quantum cryptography, this is 100% secure, guaranteed security, so they can basically realize that is the intercept eavesdropper here. I don't know if you see all this here. So now I can put everything on robots, like what you see here. And okay, so let's say that I have a robot here. The laser is on a robot. And so that's Alice. And this is Bob. I put Bob also on a robot. So now all this communication that we talked about can be done between two robots. So they can communicate to kind of a cooperative robotic task, pushing something or finding something or working together. Okay. Now, in addition to all this, we can also put the laser on a drone, and the drone is flying. And this is, the drone has a laser and has a polarizer, as you see. So basically sending, so that becomes Alice, and sending information to Bob, to ground robot or another robot in the, that is flying. Now, last thing I wanted to show you before you go is a video which is demonstrating this. I cannot demonstrate, unfortunately, today the motion of the robots, but I can show you in this video. Okay. So this video link is in the lecture notes. Can you see full screen?
Yes.
This is a different sensor that I was using before, but it's also showing the single counts, photon counts, but I'm not using that software anymore. It's an older software. There's a gimbal here, so you can stabilize the laser on the robot. Okay. Thank you, everyone. That's it for today. Is there any question?
How does Alice stay aligned?
Oh, good question. So alignment is something that we are working on. So that's kind of a research we are working. So this is what we have to work on. And also the group that are working on the drone to drone, kind of what this called, by the way, it's called quantum key distribution. So all this transfer of 0, 9, 90, which becomes horizontal and vertical polarization, the keyword for it is basically quantum key distribution. And keeping them aligned is something that has been done for laser communication. So it's available. that technology, but we have to implement it for quantum technology.
Is that what they have the gimbal for?
Gimbal is one of the, yeah, gimbal is not enough, but that's why I have the gimbal, yes.
Oh, okay.
But
Cool.
it's not enough, yeah. Good question. Okay, guys, thank you. That's it for today. You can start the test. Let me know if you have any question about the test. The test has 2 papers, articles that you need to look for the questions. We can easily find the answers to those questions from the articles just by searching.
All right. Thank you, Professor.
Thank you.
Guys. Have a
Thank
good
you,
day.
Yes, sir.
Have a
Thank you.
good day.
Thank you.
Thank you, Professor.